Hokie dokie. Welcome to Math 1026, Lab 6. Let's jump right into it. So they say in Excel, open a new Excel workbook, add tabs until you have 4 open. We're going to call each of them left sum, right sum, midpoint, and trapezoidal sum. So ignoring all the work I've done thus far, look at my mouse down here. We have left sum, right sum, midpoint, and trapezoid sum. And they also tell us to input these titles, these headers across the top. So go ahead and do that for each of the corresponding tabs, right? All right. So go ahead and do that before you get started. All right, so then we're dealing with a similar situation as the one we were dealing with in the last lab. We're dealing with some lake situation where we have water flowing in and water flowing out. We're dealing with the overall volume change as well as like the surface level, the elevation change. So we have flow coming in. We have a water flowing in. And then we have water flowing out, but also evaporation, okay? And net change, again, is inflow minus the outflow. And instead of using cubic meters per second, we're using acre feet per month. If a pond of a surface area of 2 acres has a stream feeding it at a rate of 3 acre feet per month, how much would the elevation of the pond rise in 3 months? Okay, so if the stream is feeding at a rate of 3 acre feet per month, they're asking about the change over 3 months. So first of all, if you're being fed 3 acre feet per month over 3 months, you would have 9 acre feet, 3 times 3. So if the acre feet has increased by 9, to find how the elevation of the pond would change, you would take the volume change, which would be the 9, divided by the number of acres. So you take 9 acre feet divided by 2 acres to give you 9 over 2 feet. In other words, 9 divided by 2 is 4.5. So the surface of the pond, the elevation, has changed by 4.5. It has risen by 4.5 feet, which we can see in this upside down answer here. I'll let them explain it. You can look at that on your own time. All right, so now dealing with the Excel stuff, your ideal lake also has a surface area of 2 acres. So we'll keep that in mind eventually going forward. Get my camera more on me here. There we go. So they give us functions for the in, the out, and the evaporation. So the in is the water flowing in, and then the out and the evaporation is all the water that's flowing out essentially. So there's out and evaporation. They mention to use pi in Excel. Make sure you use this pi with the parentheses like that. And then also sine squared should be input as sine of x, and then the whole thing squared. Blip, 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 blip. So your job is to determine if this mathematically ideal lake is an ideal lake or a good spot for your next vacation. So we'll talk a little bit more what that means later. Using a step size, a delta t of 0.1, use Excel to approximate the value of the integral for each of the equations over 12 months, 0 to 12. Okay, left, right, trapezoidal, midpoint, sums. They tell us the true net change in water volume is 276.34 acre feet. Use this fact to calculate the error. Use the lake surface area to calculate the change in elevation. Okay, set. Starting with this table, if you want to talk through this a little bit, the first t-value for a left sum will be 0 because we use the leftmost t-value, which if we're starting at 0, that is 0. And then for the right sum, the first t-value would not be the very first one. It won't be 0, but it would be the next in line. And if the step size is 0.1, then that next in line value is 0.1. Midpoint sum, we'll get to it eventually, but the first t-value will not be 0 and it will not be 0.1 because the first rectangle does span from 0 to 0.1. And so the x value you would use, or the t value you'd use, is right in the middle of those. So not 0, not 0.1, but 0.05 will be the first t-value for the midpoint. Trapezoidal, you'll just start at 0. Last t-value would be, so for the left sum, you would not use the rightmost value, right? You leave off the 12. So if the step size is still 0.1, the last value for left sum would be 11.9. For a right sum, it'd be 12 because you use the rightmost values. For a midpoint sum, it'd be between 11.9 and 12, so it'd be 11.95. Trapezoidal would be 12. All right, flow in, flow out, evaporation. All right, let's go to Excel and talk a little bit more about this stuff. Starting with the left sums here. Again, we start from 0. And we go all the way to 11.9. For a left sum, we include the 0, but we leave off the 12 for the t-values, right? So the in function, all you do is input this in function right where, the in first, cell is right here. And anywhere you see t, you're clicking on a 2. So that, bam. The out equation, we have 5 sine t over 12, so 5 times sine a2 over 12. Evaporation, that's the harder one to input, but this is the formula up here, okay? 10 times sine, so 10 times in parentheses, sine of, in parentheses, a2 over 12 for the t over 12, and then minus pi, which is the crazy, like pi parentheses, and then that red parentheses closes off the sine argument, and then you put one more parentheses to close off everything surrounding the sine, then you square that to represent sine squared. All right, hit enter. With all these, you could highlight all 3 at the same time if you wanted, and drag these babies down to fill in all those needed values. And then for the left sum in, what we're doing is doing the left Riemann sum, right? So you always do the width, which is 0.1, the delta t, times the sum of all the in values. So you can see that I did, 0.1 times the sum of all these values in this column. Didn't leave any off because we're only using the necessary ones. Once you have this equation input right here, you can actually drag this across, and it'll complete those 2 cells there because it'll repeat the same sort of idea for the left sum out for the out column, and likewise it'll repeat the same left sum formula for the evaporation column. All right, so in, out, evaporation. And I went ahead and put the units here in case you were curious. Oops, 1,000 acre feet. Okay. And then overall net change, that's simply doing the in minus the out minus the evaporation. This is all the water coming in. This is all the water going out in one way or another. So overall net change is 274. And then I was confused by this net change interval. They don't explain it until later in the lab, so I'll explain it to you now because that would make more sense. So net change interval is the net change of the water, but over like the individual time values. So for example, this 10 up here comes from, if we scroll over, B2, the 10 minus C2 minus D2. So you're still doing in minus out, but you do it for just those individual cells. And then likewise, or and then once you have that, you just drag this down to fill in all the rest of the values, all the way to the bottom, obviously. And basically it's calculating like each interval, each time interval's net change. It sounds like it would have been clear by the name, but also I was confused, so sorry. All right, net change error. This just comes from the overall net change minus the exact value that they told you right here. So 276.34. So we do, just H2 minus that. Again, addressing something in the last lab, they said you have to do like the absolute value of it. It's a personal preference thing at this point. I don't know. Maybe error in general is supposed to always be positive. It's up to you. I don't know. As long as you have like the value of it, I don't really care. No one should care. The error is 1.95. Positive or negative. All right, we'll talk about change in water level in a moment, but let's go ahead and start with all these for every single one, okay? And then we'll address the change in water levels. All right, so looking at the right sums now. So the right sums, again, start at 0.1, and they will make their way all the way to 12. The functions are the same. You can literally just like copy and paste them if you wanted to from the previous pages. That should work. And then you just drag these formulas down. That should be fine. Right sum in. Again, we do the same 0.1 times the sum of all the in values because we're only using the necessary ones. We don't need to leave off any. And then you can do that same trick. You can drag this across and it'll fill in all those for each of their respective columns, right? Right sum out, right sum in, yada yada. Overall net change, again, in minus the out minus the evaporation. Net change interval, again, just in minus out for that first row there. And then you can just drag it down and it'll complete the rest. Net change error, again, just the net change minus the exact value, the 276.34. Hit enter. 1.96, a positive 1.96-ish is the error for the right sum. We had negative 1.95 for the left sum. Let's talk midpoint rule. I know I addressed the t values in that little chart there a little bit. So we said 0.05 would have been the first t value for a midpoint sum because, again, the first rectangle ranges from 0 to 0.1. The first rectangle is between those two, and the height of that rectangle will come from the t value in the middle of those first two values, I guess. So halfway between 0 and 0.1 is 0.05. And it's important to remember each rectangle will still have a width of 0.1. So you'll start at 0.05, but you'll still go up by 0.1 each time. So you could do the formula of like A2 plus 0.1, or you can just type these two numbers, highlight them both, and drag this down until we're just before 12 at 11.95. If we go past 12, we're too far. We don't want to go past 12, right? So, and then the formulas will still be the same. So here I can demonstrate just copying and pasting. I think I can even, dang. You might be able to copy it all the way, all the way through. Let's try this. This will be fun. We're going to copy B2 all the way to J2. Let's check this out. Hit enter, and we can see that this copied that right. It's got the same formula, and keep in mind it's still just referencing A2, and that's correct. Midpoint sum, and these are going to be off until I drag these down here, so I'll drag this down. So highlight all three, drag the corner down, get all those function values, and now still this is calculating the correct sum. Net change, again, is still just in minus out minus evap. Net change interval, that should be doing that minus that minus that, and then we just drag that down. Where is it? All right, got all those. And then net change error should also still be right, which is amazing if that's the error, right? So net change, yeah, it was like 276 minus the exact value. That's pretty dang good. So midpoint is our winner right now. It's the lowest error, which means, it's the most accurate. Change in water level, again, we will address all together once we have each thing here. Let's go ahead and do trapezoidal. Again, I went ahead and just calculate all the function values for trapezoidal. And then, again, we're starting at t values of 0, going down to 12, getting all those function values. And I wanted to just talk through the trapezoidal sum just because it's a little more complicated. It's not that bad. You should know how to do it at this point, hopefully. Let's talk to it. Trapezoidal always starts with a 1/2 or a 0.5. We multiply by the width, which is 0.1. We multiply that by the first, so we're doing the trap sum in, so the in column. We do the first value plus 2 times the sum of all the in-betweens. We leave off the last value there, the function value. Looking up here, we can finish the function. We have 2 times the sum of all those. We want to close the parentheses on that, and then we still want to tack on. We add on that last function value. Close the parentheses, take a good look there, hit enter, and we get our trapezoidal sum in. We should be able to drag this across, and it should find the trapezoidal sums correctly for each of those corresponding columns. we do our overall net change by doing, again, in minus out minus evaporation. Hit enter, we get about 276. This is going to be a good one. Net change interval, I'll demonstrate that. We do in minus out minus evaporation over there. We drag that down. All right, and then the net change error, which would come from doing this minus 276 point, I think it's 34, which, I mean, that's going to be really close to 27634. That checks out. Yep. Okay. So which one was closer? Midpoint was 0.002. This was 0.006. So close second place is trapezoidal sum, but midpoint sum crushed it. That's crazy. Okay. Let's talk change in water level. Let me make sure I didn't miss anything. I don't know if I'm going to go over all the flow in, the flow out. Hopefully it's self-explanatory. I'll just do it for like the left sum, and you can apply it to the others, right? So the flow in, flow out, evaporation. Okay, so the flow in is the 334. Flow out is 2737. Evaporation's 32.37. Units for the calculations would have been 1,000 acre-feet. Total or I think it was it still, oh, it might not have been 1,000 acre-feet. I think I was mixing it up with the last lab. Hold up. I'm glad I actually caught that, because that could have led to confusion. Where do you confirm it? I don't know. I guess it's just acre-feet. Yeah, okay. Whew. Sorry about that. I was still in the last lab mode. Let's get rid of that before anyone tells on me. All right. Acre-feet. We're just using regular acre-feet. It's a smaller pond than the last lab, I guess. I hope there's, yeah, I don't think there was anything that even said 1,000 acre-feet in this case. Okay, sorry about that. Acre-feet. Whoops. I'm glad we went over this chart. Okay. Units are acre-feet. All right. Total inflow. Total inflow, there's only one inflow. So the total inflow, oh gosh. Stuff just lagged there. Hold up, give me a sec. Oh my gosh, my mouse is freezing on me. The computer can't handle all this. All right, what was I doing? Total inflow, there's only the water flowing in from this one river or whatever, right? So the total inflow is 334. The total outflow would be the sum of these two numbers. The 27 plus 32, whatever that is, would be your total outflow. Net change is our 274. The error we calculated, which is negative 1.5. Units for those would be what? What would that be? The units. It's still just acre-feet. Yeah, we haven't even done the water level rise. Yeah, we'll talk about that next. Yeah, that's right. Okay. Change in water level. Yeah, let's go ahead and do that for all of them. Probably could have done it along the way. All right, change in water level comes from the net change divided by the surface area. So the net change, keep in mind these units for the net change are also in acre-feet. And the water, they tell us, you know, the pond or whatever we're dealing with still has a surface area of 2 acres. So what we do is really just take the net change and divide it by 2. Because if you have acre-feet and you're dividing it by acres, the result is just feet. And that feet, the amount of feet, is telling you how much the elevation, the surface level has like risen by or changed by. So the water level has grown, has risen 137 feet, and that is crazy. Okay, so let's I think you can just copy and paste. Okay, let's copy and paste both of these, paste them where we need to. Enter, hit, oh, I gotta copy it again, hold up, copy, a paste, or just hit enter, probably slamming on these keys, sorry. Copy or control C, hit enter, 138. All right, I think these are, yeah. Okay, yeah. So for each one, we got about 137, 139, 138, and 138. Okay. Okay. Yeah, that's it. So change of water level where all the values I just read off and all the units are in feet. Which method was most accurate, which was the least? So the most accurate method we mentioned earlier was the midpoint sum. Why? Because the error was the smallest. We had 0.002, while the other errors were just slightly higher or even way higher, way higher. All right. Assuming the lake was full to begin with, should this be your next vacation spot? So assuming the lake was full, okay, we could say high tide or something like that, like it's full. Imagine a full swimming pool. Imagine a full swimming pool, and then over some time, the height of the water rises 137 feet. You wanna stay there on your vacation? No, you don't. Where am I trying to go? There we go. Yeah. So the idea is no, you would not want this to be your next vacation spot, because if the lake was full and it grew, the water level grew 137 feet, everything would be flooded and underwater, and you would not have a good time. Okay. Yeah, so like all the way over here is where they tell you to find the interval, the net change interval stuff. It's very out of place in my opinion, but then they also like tell you to use it for this next portion, so it's confusing. They could have put it maybe a little later on the Excel line up there. Anywho, so what do we do? They tell us how to calculate the intervals, so we've already done that up to this point. Now we're going to use these, we're going to plot these values in a scatter plot, highlight the time and the interval change, and then insert a scatter plot. And what we'll do is go to trend line, more options, and the whole goal is we're going to plot, I'll kind of demonstrate it with the left sum here. We're going to plot column A, the t values, and hold control. So you click on A, hold control, and click on I to highlight both at the same time. You go to insert, scatter plot, like that. And we're going to add chart element up here. Go to trend line, go to more options. You should see this little, screen right here where the bars are. Click on exponential. You want an exponential curve of best fit. Hit display equation on chart, and we get this equation right there. That's it. The whole goal is getting this equation and actually integrating it. So they say enter that function here. If we want to know the net change, we can integrate this function over the entire time interval. In other words, we'll do the integral from 0 to 12 of this function, calculate this integral, and put your answer here. So at this point, I think you should have, you should know how to do integrals like this. For demonstration purposes, I'll just do it in Desmos here. But what we're going to do is find the function, this function, do the scatter plot, do the exponential curve of best fit, get the equation for that curve, and we're going to integrate every single one of them, I think. Maybe. I don't know. Let me double check this just to make sure. Another functions, most accurate approximation. Yeah, okay, yeah. So for I guess just the left, right, and the middle, they want you to do the value of the definite integral here, and then you can write out the functions it gives you, and then error compared to the true net change, which the true net change is the 276.34. They give us the star. Okay. Let's give it a go. So for these three rectangular ones, we have the first one for the right, the left sum, I mean. Let's, how do I want to do this? Let's just go and do the same thing for the right and the midpoint. So we highlight A, highlight I, hold control, do the scatter plot, add chart element, trend line, more options, exponential, display equation. It's going to be very similar, but just slightly off. Let's do midpoint, highlight A, highlight I, insert, scatter, add chart element, trend line, more options, go to this bar thing, go to exponential, go to display equation. We get this other similar function here. Now, So like each of these functions, we have 93798, 9348, 9364. Like all these functions will be the functions in, whoops, all the functions will go here, here, and here, if that even made sense. Mouse is dragging it all over the place. But you know, the first row here, so the fitted function for each of these are the functions we just found. So the value of the definite integral, I'm going to evaluate these in Desmos real quick for each of these. Put me over there. Let's do this. Come on, left sum. All right, so for the left sum, we're doing the integral of 0 to 12. Let me show you to get this in Desmos if you want to use Desmos. At this point, you shouldn't have to, but I'll go ahead and do it anyway. Let me go ahead and talk about like what the integral would be by hand. So the integral of this, or let's start with this, the antiderivative of this function would be the same thing and then just divided by 0.132. Caught that? So the integral of this, the antiderivative would be the same exact thing divided by 0.132. The 0.132 comes from the exponent coefficient. So then you would evaluate that from 0 to 12. So you'd plug in 12 to what I just said, and then you'd plug in 0 to what I just said, and then you'd subtract the 2. All right? So this is Desmos. We're doing 9.3798 times, in this case you can actually use e because it's Desmos and not Excel, e to the power of 0.132x. Close that off, make sure to type in dx, and we get 275, 312, yada yada. Okay, so what I'll demonstrate here is the integration by hand that I was describing a moment ago. So the function for the antiderivative of this function, keep in mind we're integrating this function, which means we take the antiderivative. So the antiderivative is this times exp times the same exact thing, so 0.132x. I'll fix the x in just a second. I'll actually like plug something into it. And then we're dividing all this by 0.132, okay? So this is our function, and what we want to do is in place of x, we're going to plug in times 12, and then we're going to type in the same thing and subtract it with 0 plugged in. Sorry, I had to think about a bunch of different things at once. So we have the 12 evaluation right here, right? The antiderivative with 12 plugged in, and then we're subtracting the antiderivative with 0 plugged in. And what all I'm doing right now is just showing that this value, 275, is equal to the one we just calculated in Desmos. So 275, 312, 275, 312, that's the value. So I'll just use Desmos for the rest of them, but that's how you would do it in Excel. Okay? Okay. Ooga booga. All right. Let's do the, all right, so like in the lab now, you would plug in the value of the definite integral as 275, right? All right. And then the error to the true net change. Let's go ahead and we'll do that last. Sorry, I'm all over the place. Not much organization. Let's go and do right sum, then midpoint, then we'll talk about the error. All right, right sum. We just need to change the decimals behind the 9 to 348. And then the E to 1325. 1325. Hit enter. We get 275. I'm just going to type it out here. 275.413. 169,675. Hopefully. 413,169. 675. All right. So that's our integral value. Let's do our last one, midpoint sum. We have 9364. Yeah. All right. 9364.1322. So something like that. All right. So we get 275.262,441,932. This is our integral value. And how are we doing on time? We're almost done here. That's about 30 minutes. That's pretty solid. Okay. We have our 3 integral values. So now let's just make this bigger. We're going to type an error here. Error here. Error here. This is the integral value again. And so the error, again, comes from doing this minus the exact value that they told us, which was 276.34. So we get that. Let's just copy that. Nah, I think it's, yeah, that's fine. We'll just do this. This minus 276.34. Yeah. And the last one equals this minus 276.34. We get that. So we got about negative 1.07. We got negative negative 0.92, and then 1.027, negative 1.027. So those are all the errors compared to the true net change, right? Blah, blah, blah. So which sample point gives you the most accurate value for the net change? So I think that was the right sum, oddly enough. No, yes. Yeah, the right sum had the smallest error, at least of these 3. Curious they didn't tell us to do it with trapezoidal unless it's cut off. Yeah, I don't know. I guess you wouldn't need to. Maybe. I don't know. I wouldn't sweat it. That's pretty much it. That's the whole lab, I think. Okay. Okay. So, yeah, that's the whole thing. Let me get a good shot at all these other screens we worked on today. Got the interval graphs, trapezoidal sum. All right, I think that wraps it up. If you have any questions, please let me know. Make my screen bigger here. All right. Thanks so much for watching. If you have any questions, let me know. And I'll see you next time on Working Out Labs for 1026. All right. Bye-bye.